Hello everyone, and thanks for watching Edupedia World videos. In this video we discuss the wave nature of light, and then we move on to the dual character, which will be the beginning of quantum mechanics. One of the first scientists to postulate that light was made up of waves was a contemporary of Isaac Newton, and his name was Huygens. And he postulated a principle which is known as Huygens principle, and that explained how light was basically propagated from point A to point B, how light moved. And his principle was that, let's assume that you have a point source of light, then it will start creating waves in the radial direction. And so at any point, let's say this is the wave front. Now a wave front is a surface on which every point has the same phase, and for a point source, wave fronts are spherical because every point on the sphere is at the same distance from this point. Right. So when this surface is reached by the wave front, every point on this surface can be assumed to be a secondary source of waves. These will also give radial waves, but only in the outward direction. And so every point will basically be this source, and after a certain time, the new wave front will be obtained by the superposition of these secondary wavelets. So when you join them, you'll get another circle. When you make a tangent to them, you'll get another circle. I apologize for the drawing. But that circle will be a concentric circle with a slightly bigger radius. So this is how the waves propagate from spherical surface to a spherical surface with a higher radius, and that is that every point on this secondary surface will become its own source of waves, and the new wavefront will be seen as a superposition of these secondary wavelets. This should be a tangent here. And using this principle, he was able to explain, just like Newton, the law of reflection of light. So we'll try to derive the law of reflection using Huygens principle, and before that we need to know what a wavefront for a plane beam of light looks like. So this is a plane beam of light. If it started at some point a long distance away, then these 3 points will have the same phase, which means that the wavefronts of a perpendicular beam of light are perpendicular to that beam. And using this, we'll try to derive the law of reflection, which is that the angle of incidence is equal to the angle of reflection, and the incident ray, reflected ray, and the normal all lie in the same plane. So let's say this is our reflecting surface, and a beam of light goes in like this and is reflected like this. So our aim is to prove that this angle is the same as this angle. But instead of looking at the beams of light, what we'll do is we look at the wave fronts which are created by these beams. So instead of this beam of light, we'll have a wave front which will move like this, and eventually it will reach this point where one end of the wave front will just touch the reflecting surface, and after some time the other end will touch the reflecting surface. Let's say this distance is d. So let's call this point A, B, C. So at t is equal to 0, point A becomes a secondary source because that's when the end of this wavefront touches the reflecting surface. At t is equal to d by c, where c is the speed of light, point B reaches point C and starts becoming a secondary source itself. So when B reaches the reflecting surface, A has been a secondary source for a time t is equal to d by c. So it will create a hemispherical wavelet which will have a radius d, because there will be d by c multiplied by c. So this is d. Now any point on this wavefront will reach the reflecting surface at a time between 0 and d by c. So it will create waves of radius smaller than d. So let's take an arbitrary point on this wavefront, d, capital D, and let's say it reaches E. And at point E, it becomes a secondary source of waves itself with some radius. The radius will be smaller than d. Now I need to prove that when you join point C and the tangent to this point, then the tangent to the circle whose radius is E also touches it at the same point, which means that any arbitrary point will have a wavefront which is at the edge of this line DC. So let's say that DE is equal to X. So if DE is equal to X, we can see that triangle ADE and triangle ABC are similar because this angle is 90 degree, this angle is common between them, so all three angles are the same, which means DE by BC, which is X by D, is also equal to AE by AC, right? Because we are talking about triangle ADE and ABC. From that, I can see that CE by AC is 1 minus X by D, right? Because CE and AE together form AC. Now what we can also see, if this is G, triangle CEG and triangle CAF are also similar because this is 90 degrees, this is 90 degrees, this angle is common between them. So because CE by AC is equal to 1 minus X by D, so will EG by AF be. EG by AF is equal to 1 minus X by D, which is D minus X by D, but we already know that AF is equal to D. So that tells me EG is equal to D minus X. So the time taken to go from D to E is X by C, and the time taken for EG is D minus X by C into C. Sorry, D minus X by C. And when you add them, you get the total time D by C. So we've been able to prove, and since X was basically an arbitrary point taken on this wavefront, for every point we've been able to prove this, that it will create waves which will basically form a tangent to the line FC. So this proves the superposition of the secondary wavelets will also be a parallel beam of light because the wavefront is planar. Also, we can see that triangle ABC and triangle AFC are congruent because this angle is 90 degrees and this side is the same, and AF is equal to BC. So when these two triangles are congruent, we get that this angle is equal to this angle. And since the perpendicular to these two lines will be the normal and the incident ray as well as the normal and the reflected ray, we are able to prove that the angle of incidence is equal to the angle of reflection. Let me just draw the figure one more time. These are the two beams of light. This is the wavefront for the first beam. Let's say this is the wavefront for the second beam. Once we prove that these two angles are equal, then since this is 90 degrees and this is 90 degrees, this angle is equal to this angle and this angle is equal to this angle, which means we've proved that the incidence angle is equal to the angle of reflection. And the fact that they're coplanar can directly be seen from the figure. So we are able to prove, just like we did in the previous video for Newton, the law of reflection using Huygen's principle. So the law of reflection does not necessarily state whether light is a wave or a particle, because we were able to explain it assuming both light is a wave, which Huygens did, and light is a particle, which Newton did. But there's another experiment called the Young's double slit experiment, and it is called the YDSE for short. And this was an experiment which could only be explained by assuming that light was made up of waves. So this was one of the first few experiments which created a conflict because this could not be explained by assuming the particle nature of light. So what happens in the Young's double slit experiment is we have a parallel beam of light of a particular wavelength. So the sunlight won't do, we need a particular wavelength, and we pass it through a surface having two small slits. Everything else will be blocked, only these two slits will be open. And then we see the light on a screen, and what we see is that it forms bands, which means that at the center you obtain a certain amount of light, and then you don't obtain any light, and then you obtain a smaller amount of light here, and then again you don't obtain any light, and then an even smaller amount of light. In fact, the intensity of light goes something like this. So at the center you will have a bright spot where light will be concentrated, then you have a dark spot, and once again a bright spot, a dark spot, a bright spot, a dark spot, and so on. And the intensity of the bright spots keeps on decreasing as you move away from the center. Now this behavior can only be explained assuming that light was made up of waves. It cannot be explained assuming that light was made up of a number of particles which did not interact with each other. So we'll first try to explain these bands by using the wave theory and then see why the particle nature is not able to explain this. So let me draw the figure properly. These are the two slits of light. This is the band. The difference between the slits of light is small d, and the distance between this surface and the screen is capital D. And let's say light of wavelength lambda is coming as a parallel beam. So these are the only 2 points which will become secondary sources of light. They will start creating their own wavelets, and then any point on this surface, the light will be created by a superposition of light coming from this point and light coming from this point. And because the distance is different for these 2 points, the phase will be different. And we know that when you add two waves of phase difference, then you get an interference pattern. You get alternate bright and dark spots. So let's try to explain that properly. Let's say this is theta. By the way, another assumption in the YDSE is d by d is much smaller than 1, which means the slit width is much smaller compared to the distance. The distance between this screen and this screen is very large. And also we'll draw perpendicular from this side here. And if this is theta, we can assume that these 3 angles are theta and this is theta as well. This angle is also almost theta, this is also almost theta because this is very far away. So we can assume that these 2 points are equidistant from this point, which means the phase difference is only this distance. And let's assume that the lights are actually made up of waves of electromagnetic field. So let's say the electric field E1 is equal to E0 sine kx minus omega t. So at this point, if this total distance is x, then it is sine kx minus omega t. For the other one, too, it will be E0 sine k times x plus delta x minus omega t. Because this distance is, if these two are x, this is delta x. And the second one travels a larger distance, x plus delta x. And we may write it as E0 sine kx minus omega t plus delta, where delta is k delta x. So delta is the phase difference. And now we know how to add two waves which have the same magnitude and only a phase difference. This can be done by assuming that they are vectors, as we've seen in the 12th class videos. So the resultant will be, or the square of the resultant rather, will be E0 squared plus E0 squared plus 2 E0 squared cos delta. By the way, I have assumed that both of them have the same intensity, which will be true if the width of the slits are the same. If the width of one of the slit is larger than the other, then this will be, let's say, E01 and E02 because they will have different intensities. So this term comes out to be 2 E0 squared 1 plus cos delta. So this is the intensity in terms of delta, which is a function of delta x. And from this we can see that if delta is equal to 2n pi, cos delta will be equal to 1, which will tell us that this whole thing will be 2, which means we have bright fringes. Any point where delta will be 2n plus 1 pi, at those points cos delta will be minus 1, and then this term will be 0, which means there will be dark fringes. So whenever delta is 2n pi, delta is basically k delta x. So k delta x, whenever it is equal to 2n pi or a even integral multiple of pi, you will have a bright fringe. And when we are at the center point, obviously delta is 0, which is 2n pi, and cos of 0 is 1. So we get a bright fringe at the center, and then we have a dark spot, and then we have a bright spot and a dark spot. Notice that this is what we assumed in order to derive this result. and this assumes that light is made up of waves. And so we also know that k is equal to 2 pi by lambda. From that we get delta is equal to 2n pi, means 2 pi by lambda delta x is equal to 2n pi, which means delta x is equal to n lambda for bright fringes and delta x is equal to n plus half lambda for dark fringes. And we know that as we move away from the center, delta x keeps on increasing. So at some point it will be an integral multiple of the wavelength, then half integral multiple of the wavelength, which will be a dark spot, then integral multiple of wavelength, which is a bright spot, then half integral multiple of wavelength, and so on. So we see that the particle theory of light does not explain this, and because of this experiment, for a long time it was generally assumed that light is made up of waves. Until we came to photoelectric effect, which I discussed in the previous video. Chronologically that came after the YDSE, and so we had YDSE, which convinced a lot of scientists that light was made up of particles, but then you couldn't explain the photoelectric effect by assuming that. You could only explain the photoelectric effect by assuming that light was made up of particles. So there was this big debate among scientists, and finally it was resolved in the 1920s with the development of quantum mechanics, and that's what we'll see in the next video. Thank you.